Hello everyone, we are going to talk about the efficiency for an engine. So we are going to make the calculations in this small example exercise. First of all, I'm going to make the schema of what is happening in the machine. So this is the system, and we have two sources. So why am I considering these two sources? Because a thermal machine, by definition, is bithermal, which means that when you have a cycle in thermodynamics, when it's a thermal machine, you can be in bithermal case when you have in contact one hot source and one cold source. And this is the case for an engine. So before we start to explain what is getting inside of the system and what is getting outside of the system in terms of work and heat, we need to understand the purpose of the machine and what we provide to the machine. So when you have an engine, what you are providing to the machine as external operator is the combustion. So you are going to make combustion into your engine. This combustion is going to create a difference of pressure that is going to generate the motion of pistons, and then this is going to be generating a mechanical mechanism that's going to make your car work at the end of the process. So the first thing that was the beginning of the whole process is the heat that you provided to your engine. And this heat is called QH here. So QH is going to be positive in the referential of the system because it's received by the system as I'm providing it as an external operator. And once you provide QH, then the whole mechanism is going to be created, and this is going to be a consequence of that QC, so the hot cold. In the other side, that is in contact with the cold source. So here the heat is going to get outside of my system, so it's negative. And also something very interesting that is going to be generated is the work out. So the work is related to the mechanical energy, and the work is going to be provided by the system to the outside. So it's negative, again, in the referential of the system. And this is exactly what we want because we need the mechanical energy to be provided by the engine so that the car can work. So now we are going to define the efficiency. So the efficiency is the benefits over what you provide in the referential of the external operator. Don't forget. So it's important to understand the purpose of your machine when you define your efficiency. So for an engine, your benefits as the operator is going to be the work because it's the mechanical energy that is created by the car. So this is my benefits. And what I provided to have this is the heat for the combustion in the beginning. So this is what I provided. As you can see, QC is just a consequence of the mechanism. It's not what I provided. It's not what I get as result. So it's just here, but it's not going to be part of the efficiency in the first definition, in the first expression of the definition. So this is going to be W out over QH. But be careful here, it's important to add the fact that we are talking about absolute values. Why? Because when you consider your system and when you are making the thermodynamics calculations, you will consider the signs in the referential of the system. So here, for example, the work will be negative. But your eta, so the efficiency, is in your referential as external operator. So for you, it's something positive. So you need to add the absolute value so that you can have something that is not negative. Now the question is, what is the work? We are going to use the first law of thermodynamics. The first law of thermodynamics says that the delta U, the internal energy variation of the cycle, is equal to the work plus the heat of the cycle. It's very important here to understand that we are talking about the resultant heat, the resultant work, the resultant internal energy variation. What means the resultant? It means that you are going to take all the elements, for example, for considering the work, all the works of your cycle, add them together, and then you will have the resultant one. Something else that you will consider is the fact that delta U is equal to 0 for a cycle. So that's the definition of a cycle in thermodynamics, very important. Delta U, the resultant delta U is always equal to 0. So we're going to use these two things here. And we will then just add these two formulas together and have the result. So delta U equal to 0 equal to W cycle plus heat cycle. I'm just going to make again the schema of the situation. So we said that we have QH here positive, QC negative, and the work negative in the referential of the system. So if I replace, I will have Q cycle, W cycle, which is the summation of all the works, but we have just one work in the cycle, so it's going to be W out. Actually, I'm not going to write the sign right now. I'll make this at the end. I'm going to consider the absolute value. So W out, and then for the heat cycle, it's going to be the summation of both heats, QH and QC. Now the question is, what is going to be the sign that I'm going to write between the signs that are between the physical quantities here? So for the work, it's getting outside, so it's negative, so I have a minus. For the hot heat, it's going to be positive, so I have a plus. And for the cold heat, it's getting outside again, so it's negative. And once I have this, I'm able to express W out. That is going to be just this. And once I have that, I can come back to the definition of eta, efficiency, which was W out over QH. And all I need to do now is to replace W out by its expression. And here we go, we have the work, and then we have the efficiency of our thermal machine that is in this expression.